Hello everyone, this is the recapitulation of the live stream held today, June 21, 2025, between 2 p.m. and 4 p.m. GMT. I saw the chat of one of the attendees at the end of the live stream that my audio was very bad, and I decided to make a video 1 hour later because one attendee or one of the attendees stayed till the end of the live stream. So even though I'm a little bit tired, but I just want to sacrifice my time to make sure I make a video, at least for the benefit of those that attended the live stream and those that will see the video as well. Okay, so today we are going to discuss the epsilon-delta definition of a limit of a function. A week ago, we discussed the informal way of defining the limit of a function, and we said that the limit of a function is actually what you are getting close to. Okay, so the more and more you get close to a given particular point, okay, so where you are getting close to is what we refer to as the limit of that function. Okay, but today we're going to look into the formal and precise definition used in calculus to define what it means for a function to have a limit at a particular point. So you already know that the limit as x approaches a of f of x is equals to L. So you know that, and you know that we are trying to move, get closer to point A. So we are going to use the formal method to prove this now. So now let's go through the definition first, then I will explain all the parameters available in the definition. So let the function f of x be defined on the open interval around A, except possibly at A itself. So we say that the limit as x approaches A of f of x is equals to L if and only if for every epsilon greater than 0, there exists delta greater than 0, such that whenever this is greater than 0 but less than delta, it follows that this is less than epsilon. Okay, so I'm sure that you already understand these parts. Okay, so what this part is telling you is that if you have, let's say we have something like this. Okay, I think I can actually draw something like this. So if this is the x-axis and this is the y-axis, okay, so if you have a point, let's say this is the point here, so you can call this point A. So if you have a function, let's say this is the function f of x, for instance. So if the function is defined, okay, at point A, so you're going to have the output here. Okay, so and if the function is not defined here, so you won't have any output here. So there's going to be a kind of gap or a hole or a jump in the graph. Okay, so but whether the function is defined at A or not, so you can always get the limit because we are dealing with the distance around A, okay, either from the left or from the right. So when it comes to limit of a function, so that is what this particular statement is saying. Okay, and A is excluded here. Okay, so if the function is defined at A, so that means the f of A and the limit of the function will be equal. That's the implication. But if the function is not defined at A, so the limit and the function, the limit of the function and f of A will be different. So that is just the difference between the two. Okay, so this side has been explained. So now let's come here. So if this is true, then we say that the limit as x approaches A of f of x is equals to L if and only if, so the limit will exist if and only if this holds, that is, for every epsilon greater than 0, epsilon must be positive. So very soon I will tell you the meaning of epsilon, and I will tell you the meaning of delta. So if epsilon is greater than 0, so automatically delta will be greater than 0. Okay, so this statement here is like a universal quantifier. So if this one exists, so this one must also exist. So such that whenever this is greater than 0, okay, but less than delta, it follows that this must also exist. Let's start with the last two statements, because this is what many students do find very confusing. Okay, so I will try to explain them. So here the first one is this. So what does it mean? Okay, this particular one, that is the absolute value of x minus a. Okay, so this is like the closeness. Okay, you can call it closeness to, so closeness to point A, so I can call that. Okay, then what about this particular one, the absolute value, okay, of the absolute value of f of x minus L, okay, is like the closeness to the limit L. Okay, now, so if you have this now, the absolute value of x minus a, okay, less than delta, okay, it means the closeness is within the value of delta. Okay, is within delta. So that is what it means. And this one, if you say the absolute value of f of x, okay, minus L, okay, is less than epsilon, so this one means the closeness is within, within here is within epsilon. So that is what it means. Okay, now you know the meaning of this now. Okay, and you also know the meaning of this. So what is delta? What is epsilon? So that is the next thing we need to do. So don't forget that the function is defined around open interval of a. So let's say from here, from the x and y axis here, so we have the open interval here. Okay, good. So this is point A. Okay, so from here, from this point to this point is your delta. Okay, so you can write it as delta, and from here to here is also delta, like this. Okay, is the value of delta, because they are equidistant, okay, from point A. So that is why you have this. And of course, this particular point now will be a plus delta, and this particular point will be a minus delta. Okay, so that is what we're going to have here. So the delta is just the distance from the open interval to point A, okay, like this. And you can also call this one radius. Okay, you can also call it radius, something like this, because they are equidistant around A. Okay, so that is delta. And what is epsilon? So epsilon will be here. So here it can be f of x, and it can also be the limit. Okay, earlier I told you that the function value and the limit value can be the same and can be different. Okay, and I told you the condition that can make them to be the same and the condition that can make them to be different. Good. So I can have the function here and I can have the limit here. Okay, now, so if you have the delta here, so the limit, the epsilon now will be, let's say we have the point here. So don't forget that you have open interval here. So any number here can generate something here. Okay, any number here can generate something here. So I have another point here. Okay, since you have an open interval here, so you also have an open interval here too. That is, a value you pick here will surely produce a value here. Okay, that will be very close to the limit. Okay, so that's what I'm trying to say. So this between this limit and this gap, it is where you have the epsilon. So let me write that again. So you have the epsilon here. So you have the epsilon here. So automatically this point here, okay, will be L plus epsilon. Okay, and this point here, okay, will be L minus epsilon. Okay, so I think I can remove this one now for clarity's sake. Let me just remove this, then I will rewrite this. Good. So this point here will be L minus epsilon. So epsilon will just be, if you pick a value here, which is a delta, so it will surely generate something here. Okay, so this is point A. So the closer you get to A, you have a point here. Okay, you have many points here rather. Okay, so you move towards A, that is the closeness, and delta will be that value. So as you get closer to A here, so depending on the graph, let's say the graph is like this, for instance. Okay, if the graph is like this, so we have something here. So if you pick any point here, okay, so the point here will give the output here, will get closer. As you are getting closer to point A here, so you'll be getting closer to the limit from here. Okay, so also if you are getting closer to A from here, from the right hand side, okay, so the output will be here and you'll be getting closer to the limit from here. So that is what delta and epsilon do respectively. Okay, so now I have explained delta and I have explained epsilon. I have also explained this, that is, this is the closeness to A, which is within the delta. Okay, and this is closeness to the limit, which is within the epsilon. As you can see here, once you understand this graph, this definition will be clear to you. So in other way, we can say that what these two last statements, that is this and this, these two statements, what they are trying to tell us is that I want to get closer to the limit. Tell me how you want to get closer to the limit. So that is what this one is telling you. Tell me how close you want to be to the limit. And this one is telling us that I will tell you how close you must be, okay, to the point A. So that is what this is telling you. So don't forget that as you get close and close to A, so you get close and close to to the limit. So that is what you can say now. So tell me how close you want to be to the limit, then I will tell you how close you need to be to you must be. This one is like asking a question. Tell me how close you want to be, then I will tell you how close you must be here. So it means that this delta here is the most important thing. Once you know the value of your delta, so automatically you will know that the limit must exist, because the value of this delta must get closer to the limit. So that is it. And if you are asked to prove that the function of a limit is a given number, okay, so you want to prove that the limit exists, once you get the value of the delta, you are done. Because once this one is true, so there must surely be an output that is closer to the limit. So that is what we are saying here. And if you see this definition again, you will see that once this one is true, look at the phrase here, it follows that this one must be true, this particular one. Okay, so that means this one depends on this. Okay, so if this one is true, that is, you know the value of your delta, then the limit must exist. So that is just the summary of the definition. So I think I can scroll down a little bit and give you a quick summary again. So if you have something here again to make it clearer, then we'll go and solve some questions. Okay, so here now, so this is my y-axis and this is my x-axis. Okay, so I have a point. Let's roll. Okay, good. So I have a point here. This is point A, and I have an open interval around this A. Okay, so from point A to this point here, the distance here is what we refer to as delta, and the distance here is also what we refer to as delta. Okay, we are good. Okay, so if you have point A, so you're going to have the limit here or the f of s depending on what you are doing. If this one is defined here, so this place will also be f of x. Okay, but if you are getting closer to A, then this point will be your limit. Fine. Now, so if I have this graph again, this straight line, okay, so here is my delta. Any value you have here is called delta. So if I come here now, for instance, okay, I'm coming, so let's say this one will be mapped to this. So I want you to understand better. So if I pick a point here which is within delta, so this one will come here now. You can see it will come to this one. Can you see it now? So that is it. Let's say this is the first one here, for instance. This one will be the first one. Okay, so this is where we are saying that, okay, this point will be L minus E, for instance, the epsilon. Okay, so that means any value I have from here, between here and here, will surely be an epsilon value that will be produced from this. Like see, all the values here will be epsilon. If I take another one here, it will come here, so it will give me epsilon. So if you can see that I'm getting closer to A, okay, so it will give me a value here. So I'm getting closer to A. So the more and more you get closer to A, okay, so the delta value will produce an epsilon, and it must be here. Okay, so what I've just done now, like getting closer to A and having different points here, and you can see that the points are also moving up here, and the point, each of the points is under epsilon, that is within epsilon. So that is the meaning of this statement. F of x minus L must be less than epsilon. Okay, now you can see that if from here, from the x-axis, I keep on getting closer to A. Okay, so that is the meaning of the statement. X minus A, okay, is less than delta, because the more and more I get closer to A, okay, so that is the delta value. Okay, so each of these will represent the delta. So it's still within the delta, even though I'm getting closer to A. Okay, so that is what this statement is saying. And of course, from here, you can see that it is greater than 0. Okay, so that means 0 will be less than this. And of course, this one too, this starting point, you can see that is greater than 0. Of course, so this one too will be greater than 0. Okay, so of course. So now that is what we're just saying. That is it. Tell me how close you want to be here. Okay, that is epsilon. Okay, then I will tell you how close you must be here. So if I get the value of the delta here, automatically I must get the value of epsilon here. So that is it. Okay, it will tell me how close I need to be here. Okay, so this is from the left. Okay, this is from the left hand side. So if I want to take it from the right hand side here, okay, I can do the same thing. If I want to take it from the right hand side here, okay, that means I'll be coming like this. Okay, so from here I'll be coming, this is an open interval, I'll be coming like this towards A from the right here. Okay, so don't forget that each of these, anyone I pick here is my delta, because this is the region for the delta. Okay, so if I pick one here, for instance, okay, it will come here. Okay, let's draw something here, and this will generate something here. Okay, so let's assume that this is the starting point now. So this will be a point, and then this point we can call it, because the distance between here and here is our epsilon, so which is equidistant to this one too. Okay, because we have equal distance here between this and this. Okay, so you must have equal distance here too. So this will be epsilon and this will be L plus epsilon. Okay, here. Okay, so that is it. So if I pick another one here, it will be delta value. Okay, it will give me another value here. So this value will fall under epsilon. Okay, so if I continue to pick like that, okay, so I'll be getting this. So that is just literally what we are talking about. Okay, so now this one is responsible for how close you want to be to the limit, and this one is responsible for how close you must be to the given point for you to get that value. So this is the typical explanation I can give you. Okay, so these last two statements, let's scroll up a little bit. Okay, that is this and this. Okay, is that this one is telling you, tell me how close you want to be to the limit, then I will tell you how close you need to be on the x-axis, that is the delta. Okay, tell me how close you want to be to the limit, then I will tell you how close you must be to the given point. Okay, so I haven't said this, so we can now go to example number 1. So this is the first question, and the function here is a linear function. As you can see, f of x equals to 3x plus 1. This is a linear function. So if you want to prove this in an exam, so you have to give the conditions first. That is, for every epsilon greater than 0, so it's good to always write this. So there exists, okay, this one means there exists a delta value which must also be greater than 0. So it's compulsory. Okay, and then don't forget that I said this is a universal. This one is a universal quantifier. So why this one is existential quantifier. So okay, so then if for every epsilon greater than 0, so there exists a delta value greater than 0. Okay, so such that 0 is less than the closeness to a. So how do we write the closeness to a? It's like this: x minus a, the absolute value of x minus a, so which must be within the delta value. So if this is true, so it follows, okay, that the absolute value of f of x, okay, minus the limit must fall within the epsilon. So this is very important. You must write this before you start. Now, from the question, we know that the given point is a equals to 2, and we know that the limit L is equals to 7, and we know that the f of x, okay, is equals to 3x plus 1. Okay, so where we always start from, you always start from here. Okay, so all right, so using the absolute value of f of x minus L is less than epsilon. Let's substitute the values, that is our parameters, into this now. So ordinarily, you may want to do the simplification first, okay? But you can just substitute directly and simplify, okay? So this is what I'm saying. So if you write this, it implies that the absolute value of f of x, that is 3x plus 1, okay, sorry, minus L now, that is minus 7, okay, is less than epsilon. So let's simplify this. So it implies that 3x plus 1 minus 7, that will be minus 6, okay, is less than epsilon. Okay, so if you have this now, so I can factor out this. So what is common here is 3. It will be the absolute value of 3 into x, then minus 2. Okay, is less than this. Okay, so that means, let me write something here for you to understand. So this absolute value of f of x minus L has been simplified to absolute value of 3 into x minus 2. Okay, so if you are seeing 3 into absolute value of absolute value of 3 into x minus 2, you are seeing this. Please take note of that because we just simplify this to this. Okay, fine. Then there is something I'm going to do now. So I'll still make reference to this later. Okay, I'll make reference to this. Just take note. Okay, so here it implies that there's another thing that I want you to take note. If you have the absolute value of a product, that is A times B, is the same as the absolute value of A multiplied by the absolute value of B. Okay, so take note of these two. I'll be using something like this. Okay, so as I prove the limit. Okay, so this one I can say it implies that the absolute value of 3 multiplied by the absolute value of x minus 2 is less than epsilon. And of course, we know that the absolute value of 3 is 3. So this will be 3. Then into x minus 2 is less than epsilon. Okay, so I can divide both sides by 3. So that implies absolute value of x minus 2 is less than epsilon over 3. Okay, so if you compare this with x minus a, that is x minus a, okay, the absolute value of x minus a, so which we said is less than delta. Okay, so you see that it is the same as x minus, our a is 2, so it will be x minus 2 less than delta. So it means that this x minus 2 is less than delta, okay, and this one too is less than delta. So if you compare them, you see that delta, this delta here, is equal to epsilon over 3. So that means I can choose my delta. Okay, so let me go like this. So it implies I can choose, so let's say we choose delta. Okay, I don't need to write, let me write this simple. So I choose delta to be equals to epsilon over 3. So this is the value of our delta. So once you get this, to some lecturers, you are done. Because once you get the value of delta, it follows that f of the absolute value of f of x minus limit must, okay, be less than epsilon. So that is what you want to prove. Okay, so once you get the value of this, okay, it tells us that this one is true. Okay, so let me show you the graphical representation. It's like you have the y-axis here, okay, and you have the x-axis here. Okay, so now what this one is telling you is that at point a equals to 2, so this is what you have here. So we have the open interval around 2. So this from here to here is our delta, and here it is just, let's say, epsilon over 3, and it could be from the left, it will still be epsilon over 3. So that is where our data is coming from. So don't forget that once you have this data here, automatically, so the function will get closer to the limit. That's the meaning, either from here or from here. Okay, so and within the region it will be epsilon. Okay, it will fall within epsilon. That means it will be less than epsilon. So the closeness here, okay, along within this open interval, okay, will automatically give us the closeness to the limit here, which is the the epsilon, less than the epsilon, because it will fall within this region. It will fall here. It can be any part of here, and it can be any part of here. So if it is within epsilon, that means it is not up to epsilon. So it is less than epsilon, because everything here is epsilon and it's taking a part. Okay, so it will be less than epsilon. So that is why I said once you get this, you are done. But some lecturers still want you to do something. They want you to just show and use your they want you to use your delta to get something like this here, this particular one. They want you to get something like this at the end. So no troubles. Okay, so I can now say part 2 now. So we can go to the part 2. So in the part 2 now, there's something like part 2, but I just want you to know that you want to start another section of the proof. Okay, so here we want to use the value of delta. So what I will just say is this. I'll write that same statement again. So don't forget that we have the absolute value of f of x minus L is less than epsilon. So don't forget, if we scroll up a little bit, I told you that I'll be making reference to it. You can see from the top right hand side here. So that absolute value of f of x minus L is the same as the absolute value of 3 into x minus 2. Okay, so that is it. So now I'll just do a side something here. Let me just do something, side work here. So if we say that the absolute value of x minus a is less than delta, okay, so if we have 3, the absolute value of 3 into if you have 3 into absolute value of x minus a, it will be what? So it will be less than 3 delta. So that is the implication. So don't forget that this one here, this 3 times absolute value of x minus a is what I have here. It is this one, right? So that means I can say that this particular expression now, which is equivalent to this, is less than 3 delta. So instead of writing this expression now, okay, so I will use this one. So I will say 3 times the absolute, instead of using this one here, okay, let me write this one so that you understand what I'm trying to do. I will write this one here now. This one, I will write it. So it will be 3 into absolute value of x minus a, okay, less than 3 delta. So instead of this now, okay, so I will write this because they are the same. So I'll just say the absolute value of f of x minus L, okay, is less than 3 delta. So that is how to bring it in. I hope you understand it now. Fine. So I can scroll up a little bit. So, but we know the value of the delta. We chose delta. So recall that we chose delta to be equals to epsilon over 3. So if we substitute here, that means we have the absolute value of f of x minus L is less than 3 times delta is epsilon over 3. So this one, we cancel this. Then you see that f of x minus L is less than epsilon. So this is the end of the proof. So it has been proven. So you can see that when we use the value of this data, okay, it gave us an output that is very close to the limit, okay, which is less than the epsilon, as I just explained here. So that is what it's saying. So this epsilon over 3 here, automatically it will give us a portion here. It will give us an output here, which is less than epsilon. Because let's say epsilon is from here to here. So the whole of this is epsilon, okay, and you're not getting a point here. So that point will be less than the whole of epsilon. You understand? So that is what I'm trying to explain to us. So in the next video, we are going to, on the next page, we have another question. So I want you to practice this. So I can just show you the introduction part of it. As usual, so we need to write all the given parameters. But before then, you have to write this statement. For every epsilon greater than 0, so there exists delta that is greater than 0, such that if the closeness to A written as this is greater than 0, written as this, and is less than delta, written as this, so it follows that the absolute value of f of x minus L must be less than epsilon. So this is what we want to show by the time we get the value of our data. Okay, so it will be very easy for us. Then the parameters, we have the value of a to be equals to 1, x approaches 1, then the limit is equals to 3, and the function f of x is given as 5 5x minus 2. Okay, so if you start from here using this, the absolute value of f of x minus L is less than epsilon, then that implies f of x, which is 5x minus 2 minus L, that is 3, must be less than epsilon. Okay, so if you try to simplify this, so you get 5x minus 5, that's absolute 5x minus 5 less than epsilon. So I can factor out 5 here. So the absolute of 5 into x minus 1 less than epsilon. So scroll up a little bit. Okay, so it implies that absolute value of 5 multiplied by absolute value of x minus 1 is less than epsilon. So it implies that 5 multiplied by absolute value of x minus 1 is less than epsilon. So if you compare this with absolute value of x minus a, and our a here is 1, is less than delta. Okay, so if you compare it with this, so you see that, okay, from there we need to take a step further here. This will be absolute value of x minus 1, so it's less than epsilon over 5 when you divide both sides by 5. So you see that this is the value of our delta, so we can choose delta to be that. Okay, so let's go up. So we choose delta to be equals to epsilon over 5. Okay, so once you have this one, you are done. To some lecturers, but some lecturers want to see you test this delta, so they want to see the final statement. So that will take us to the same place we started from. So don't forget that this particular statement here, this particular one here, so let me circle it for you, is the same as this. So the absolute value of f of x minus L is the same as this. Okay, because we simplified this from the beginning, we simplified it to this. Okay, so it's less than epsilon. Now, so let's take something from here. We need to pick something from where I circled. So remember that the absolute value of x minus 1 is less than delta. Okay, so that is from absolute value of x minus a is less than delta, and our a is 1. Okay, so that is why you have this. So it follows that, or it implies that the 5 times the absolute value of x minus 1 will be less than 5 times delta. Okay, so that means this particular expression here that I told you that is the same as this. Okay, so is less than 5 delta. I can write it, so I can say, since this one is less than 5 delta, so this particular must also be less than 5 delta. So I'll write the absolute value of f of x minus L, okay, so is less than 5 delta. So that is it. Okay, so I think it's pretty easy then. Okay, so we can now substitute the value of our delta. So it implies that the absolute value of f of x minus L is less than 5 times our delta is epsilon over 5. So this will cancel this. So it implies that the absolute value of f of x minus L, okay, is less than epsilon. So this is what some lecturers want to see. Okay, so you just make use of the value of your delta and get this. Okay, so you can check your textbook or anywhere you can get questions. So just try to do the same thing. So for a limit of linear function, Okay, for limit of a linear function, you can always follow the same step like this, so nothing special. So let's go to a quadratic function. So as usual, you have to write the first statement. So for every epsilon greater than 0, so there exists delta that is also greater than 0, such that the closeness to the given point A, written as this, is greater than 0, written as this, but less than delta, written as this. So it follows that the absolute value of f of x minus L is less than epsilon. So given that x a is equals to 1, then the limit L is equals to 3, and the function is now a quadratic function, which is x squared plus 2x. Okay, so using the absolute value of f of x minus L less than epsilon, it implies that the absolute value of x squared plus 2x minus L, which is 3, is less than epsilon. So it implies that we can actually factorize. We can factorize this. This is a quadratic expression. Okay, so I can say this. It will be the absolute value of x squared minus x, then plus 3x minus 3. Yeah, so it's less than epsilon. So it implies that, so x into x minus 1 plus 3 into x minus 1 is less than epsilon. It implies that the absolute value of x plus 3, okay, multiplied by x minus 1 is less than epsilon. Okay, so let's go down a little bit. Okay, I think it's too much. Okay, like this. So don't forget that we can write this as the absolute value of x plus 3 times the absolute value of x minus 1 is less than epsilon. If you observe very well, you see that this is very close to what we did under linear function. So the only difference here is that here we don't have a constant, so we cannot divide both sides by absolute value of x plus 3, so we can't do that. So because our delta will depend on x, and we don't want that to happen. So what we need to do now is to take a unit step towards this. So this is what we need to do. We need to take a step towards this. So I will write taking a step towards taking a unit step to absolute value of x minus 1. Okay, comma. So why am I taking a unit step, okay, to this closeness? Is because I want to find the value of x so that I can get rid of this one. Okay, so that is what I need to do, and I need to make sure that I need to make this to be very large. So I will show you what I mean by that. Okay, so if we take a unit step to this, okay, so that means the absolute value of x minus 1, this particular one, will be less than 1. Okay, so you can use any other number. You can use 0 points, any number, but 1 is easier. Okay, 1 is easier. So if you do this, so from my video, okay, I explained that you need to understand, during the live stream rather, I said you need to understand these, as in how to simplify or how to split the absolute value functions. Okay, and I told you that I have 2 videos regarding that on my YouTube channel. so you can check. Okay, but the simplest way to express this is to say that minus 1 is less than x minus 1, then x minus 1 is less than 1. So if you don't understand this, please kindly go to my YouTube channel and look for the playlist titled absolute value functions. Okay, so now I want to get x, so I need to add 1 all through. So if you do this will cancel this, so that means 0 is less than x and x is less than 2. So don't forget that I want to make this to be to be big. Okay, so if I use 0, that means I'm going to have 0 plus 3, that will be 3. So I'm multiplying this by 3. So compared to when I use 2 plus 3, 5 times this, so this will make it bigger. So I need to use x to be equals to 2. Okay, so that means I will say, so that from here now, so I will write the absolute value of 2 plus 3, okay, multiplied by the absolute value of x minus 1. So we already know that this one is less than delta. Okay, so that is why we're not substituting for this. Okay, it's less than epsilon. Okay, so scroll down. So this will be modulus, absolute value of 5. So this is modulus in vector. So we have absolute value of 5, which is 5, then multiply by x minus 1, which is less than epsilon. Okay, so from here, some of you may be somehow concerned, why would this one be less than 1? The explanation I can give you is that, the whole of this particular one, okay, is within delta. Okay, let's come again. So let's say this is the open interval, for instance, and this is 0.1, because we are giving the value of a to be 1. So don't forget that from here, okay, to here will be our delta, for instance. Okay, so and this x minus 1 is the same as s minus a, so is the one responsible to generate value of delta here. Okay, so if, for instance, now x minus a, in this case x minus 1, now let's say it is this particular one. So let's draw it here, this particular one. Okay, so if you now take a step towards this one now, so it's going to make it smaller. Okay, so it will make it to be smaller. Okay, let's say it is here. So if you take a step towards this one now, towards that x minus 1, don't forget that x minus 1 is responsible for generating each of these line, and it can be anyone. So if you take x minus 1 to be this, okay, and you take a step towards this, okay, so this particular x minus 1 will be less than that particular step you take towards it. So that is what I'm saying. So know that this particular one, okay, x minus 1 is within delta, so it's going to generate the value of your delta as well. Okay, so that is what I was trying to do here, that when you take a unit step towards, okay, let me scroll up a little bit. When you take a unit step to this, okay, so this will be less than 1. It's like we are reducing it, so automatically it will be less than 1, and you can simplify this. Okay, so I just have to explain that so that you don't get somehow confused. Okay, so let's proceed. So now I can now divide both sides by 5, so it means the absolute value of x minus 1 will be less than epsilon over 5. Okay, if you divide through by 5. Okay, so I'm sure this is not new to you now. So if you compare this with x minus absolute value of x minus a less than delta, you will see that we can choose our delta to be this. Okay, so that means it will be this, but this will not be only the value of delta. Okay, because we took a step, okay, towards x minus 1. It can be forward, it can be backward, it will be the same thing because it is an absolute value. Okay, so that means our delta will be between this 1, the value of 1, the unit we took towards absolute value of x minus 1, and this epsilon over 5. So delta will be in between them. Okay, it will be in between them, between this one and this. It will be between. So that is why we have to write that, okay, our delta, okay, will be equals to, we have to take the minimum value here. So we don't know, so we just write it will be equals to minimum value of 1 and epsilon over 5. Okay, so because the delta, you can see from my illustration here, so this one, this a step unit you took towards absolute value of x minus 1, okay, and the value of delta, this epsilon over 5, okay, that is where will be the location of our delta. Okay, so that is what I'm trying to explain to you. So we need to take the minimum value here. So let's roll up. So you can, so once you get this one, you are done. Okay, you are done. But some lecturers want to see the final part of it. Okay, so what we can do now, in this case, we are going to start from where we took a step towards absolute value of x minus 1, that is from here. So that is what we're going to use. So see what I'm going to do now. Okay, I will say that the absolute value, okay, before then we have to choose the smallest one here. So I will assume, okay, you can just say that let 1 to be less than or smaller than epsilon over 5. So if this occurs, that means 1 is smaller than this now. Okay, so you can choose anyone. You can say epsilon over 5 is less than 1 and you test it. So if you cannot proceed, okay, so that means epsilon is not less than 1, so you have to come back and do the other one. Okay, so for instance now, for now I said let 1 to be less than epsilon over 5. So by the time I walk through and it leads to a wrong stuff, okay, so I just have to come back and use epsilon over 5 is less than 1. Okay, so that is what you just have to do. So I don't know which one is smaller. It could be this. So that's why you have to test the first possibility. If the first possibility fails, then you go to the second one. So for now, I'm saying that 1 is less than epsilon over 5. So it implies that if I multiply through by 5, it implies that 5 is less than epsilon. Okay, so take note of this. I'll come back to this. So then we can now go to the second part now. Okay, so if you know that if the absolute value of x minus 1, okay, is less than 1, okay, from the step we took, okay, so now this is our function now. Okay, so we can say that 5, okay, let me write here. So okay, let me just do the rough work here. So if the absolute value of x minus 1 is less than 1, then this is our function. Don't forget, this expression is equal to the absolute value of f of x minus the limit. So don't forget. So if this one is less than 1, automatically 5 times the absolute value of x minus 1 will be less than 5 times 1. That's the meaning. And don't forget, this one, as I said, is the same as the absolute value of f of x minus 1, minus L rather. Okay, so that means instead of writing this one now, I'll write this one. I will say the absolute value of f of x minus L is less than 5. Why? Because 5 multiplied by absolute value of x minus 1 is less than 5, and this is equals to this, so it will be less than 5. Okay, but we said from here 5 is less than epsilon. Okay, so that means we can say that the absolute value of f of x minus L is less than epsilon. So this is the final part of your proof. So it has been proven that the limit of the given function is actually 3. Okay, so that is what it means. So this one is for you can practice. Okay, so the same method, you can just do this one. I'll just give you the starting parts and then you can finish it up yourself. So here you have to write the first statement for every epsilon greater than 0. So there exists delta. Okay, so there exists delta, okay, which is greater than 0, such that the closeness to A is greater than 0, written as this, and is less than delta. If this is true, it follows that the absolute value of f of x minus L must be less than epsilon. So that is what it means. So the parameters, A is equals to minus 2, then L is equals to negative 1, then f of x is the quadratic function, which is equals to x squared plus 4x plus 3. So using this, the absolute value of f of x minus L, okay, less than epsilon. So you have this, f of x is x squared plus 4x plus 3 minus the limit, which is minus 1. Okay, so is less than epsilon. So you have to add this together. This will be 4. So it implies that the absolute value of x squared plus 4x plus 4 is less than epsilon. So it implies that the absolute value, so this quadratic function, you can factorize it to be x squared plus 2x plus 2x plus 4 less than epsilon. I've almost finished everything for you. So this will be the absolute value of x into x plus 2 plus x into x plus 2 less than epsilon. Then is equals to x, sorry, this is 2, okay, so into x plus 2, sorry, to be x plus 2, then into x plus 2, okay, then less than epsilon. So this one, what does it mean? So you can say that this implies that the absolute value of x plus 2 then squared is less than epsilon. So for this one now, so what can you do? So you need to, if you compare this one, the value of our A is equals to minus 2, okay? So if you compare this one with x minus A, is less than epsilon, okay, and the value of A is minus 2, so that means this into x minus 2 like this, okay, so is less than, sorry, this one is less than delta, so it will be less than delta here. So from here now, if you see the correlation between them, so you can just finish this up and you get your data from here, and so that is just what I can do. So you can finish it up. So let's go to the next one. I'm getting tired a little bit. Okay, I think this is the last one. So, and I will leave this with you. Okay, so sorry, I will leave you with this to practice. Okay, I will do this. So this is a cubic function. Okay, so how do we go about that? It's very similar to that of linear and the quadratic. Okay, so it's just how to simplify the expression f of x minus L. That is just the key there. Okay, so here, so the normal stuff is to say for every epsilon greater than 0, so there exists delta, okay, that is greater than 0, such that the closeness to the given point A, okay, written as x minus A, is greater than 0, written as this, and is less than delta. Okay, so if this is true, it follows that the absolute value of f of x minus L is actually less than epsilon. Okay, so I haven't written this. So the next thing you need to do is to write the parameters. A is equals to 1, so that is where x is approaching. Okay, and L is equals to 0, the limit, and the f of x, which is the given function, is equals to x to the power of 3 minus 3x plus 2. So as usual, using x to the power of 3 minus 3, using the absolute value of f of x minus L less than epsilon. I'm sorry, I'm a little bit tired. So this will be f of x now, which is x to the power of 3 minus 3x plus 2, then minus L, which is 0, is less than epsilon. Okay, so this implies x to the power of 3 minus 3x plus 2, which is less than epsilon. Okay, so now we need to factorize this. Okay, so this is a cubic expression. Actually, you can use two ways to do it. So one, you have to use long division, and the other one, you just have to simplify it. Okay, so I will show you the two methods. Okay, since this approaches 1, okay, so that means we can say that x minus 1 is a factor. So we can use long division here. Okay, so x minus 1, then put x to the power of 3 minus 3x plus 2. Okay, so x to the power of 3 divided by x, it will give you x squared. Okay, so you write x squared here, times x squared times x, it will give you x cubed. Then x cubed times minus 1, x squared times minus 1, it will give you minus x squared. So if you subtract, this one will turn to minus, and this one will turn to plus. So this and this will go. So we are left with x squared minus 3x. Okay, so x squared divided by x, that will give us x times x squared, x times negative 1 minus x. So if you subtract, this will turn to minus and this will turn to plus. So this will cancel this. So we are left with minus 3x plus x, that is minus 2x. Then we need to drop 2, that will be plus 2. So minus 2x divided by x, that will be minus 2. Minus 2 times x, that will be minus 2x. Minus 2 times minus 1, that will be plus 2. So if we subtract, this will become plus, and this will be minus, so everything will be 0. Okay, so that means we have x minus 1 into x squared plus x minus 2. So this is quadratic expression, so because of time factor, so if you factorize this, it will give you x minus 1. So this will give you x minus 1 into x plus 2. So mechanically, we're going to have x minus 1 squared into x plus 2. So this is one way of simplifying this. Okay, so another way would be to rewrite this. So let's say x cubed minus 3x plus 2. So let's split this into 2, that is minus 3x. So it will be x cubed minus x minus 2x plus 2 Then you can factor out x here from these two terms. That will be x into x squared minus 1. Then from these two, you can factor out 2 minus 2 into x minus 1. Okay, so but we have x squared minus 1 here, we have x minus 1 here, so we are not done. So but this one is like difference of two squares, because you can actually write this one as 1 squared. So we have difference of two squares, so we can write it as x into x plus 1 into x minus 1, then minus 2 into x minus 1. So we can now factor out this now, x minus 1. So that means we have x minus 1, okay, into x into x plus 1, okay, minus 2. So this is what we have here. Okay, so this is what we have here. So from here now, we can now simplify this further. X into 1. So this will be x squared plus 1. So x squared plus 1x rather, which is x, then minus 2. Okay, you can see that we are back to this place now from the left hand side here. So we are back. So this one will also give us x minus 1 squared into x plus 2. Okay, so you can use any of the two methods. Okay, in case you don't know long division, so this will be helpful. Okay, so let's come back here. So this will be the same as x minus 1 squared into x plus 2 less than epsilon. Okay, so here we can split it into 2 as well. You know that this will be the absolute, let me write this one first, of x plus 2 multiplied by the absolute value of x minus 1 squared, so it's less than epsilon. Okay, so the challenge now is this: I cannot divide both sides by this, so I have to use the same idea. Okay, so as usual, so taking one step, just like what we did under quadratic, taking a unit step to the modulus, the absolute value of x minus 1, like this. Okay, so that implies absolute value of x minus 1 is less than 1. So that is the meaning. So, and you can split this into minus 1 less than x minus 1, and then x minus 1 less than 1. So add 1 here, add 1 here. So I think you should understand it from here. If you add this will be 0, this will be less than x, and this will be less than 2. So of course we want this expression to be bigger, so we need to choose 2. I think you should understand this by now. So I'll just write this one now. So that is from here. So I have to write this. It will be absolute value of x is 2. 2 add 2, that will be 4. Okay, multiplied by the absolute value of x minus 1. Okay, x minus 1 squared, which is less than epsilon. So let's scroll down. The absolute value of 4 is 4. Then multiplied by absolute value of x minus 1 squared less than epsilon. So we cannot divide both sides by 4. So that will leave us with the absolute value of x minus 1 squared less than epsilon over 4. So we can take square root of both sides. So that will leave us with absolute value of x minus 1 like this less than square root of epsilon over 4. So we can simplify that, which implies that absolute value of x minus 1 is less than root epsilon over 2. Okay, so you can see that x, this one is less than delta, so automatically this will be our delta 2. So but don't forget that we took a step towards this, so automatically our delta in this case will be the minimum between 1 and root epsilon over 2. Okay, so once you have this one, you are done. You can get your full mark. But we want to test further. So I will say 1 is less than root epsilon over 2. So I told you, that means I'm saying that 1 is smaller than this. So you can say this one is smaller than this. If it doesn't work out, then you come back to this one. So we have two options. So you just have to say let's, okay, this. Okay, it implies that if I multiply 2 by 2, it implies that 2 is less than square root of epsilon. And then if I take square of both sides, okay, so that means 2 squared will be 4, then it will be less than 4 will be less than epsilon. Okay, so I need this. So this is very important. Okay, so I need to do the final part now. The absolute value of x minus 1, okay, is less than 1. So if we take it from here, this particular one here, okay, so that's what I'm saying. So that implies that since this one is less than 1, then 4 times the absolute value of x minus 1, or this squared, okay, will be less than 4 times 1. That is what it means. But don't forget that this expression here, let me write this very well. So don't forget that this expression here is the same, this particular one is the same as our absolute value of f of x minus L, okay? So it will be less than 4, okay? So I just substituted, okay, this for this, okay? So we can say, but 4 is less than epsilon, as you have here, from here. So can I say that therefore the absolute value of f of x minus L, okay, so is less than epsilon. So this is the final part of your proof. So it has been proven that the limit of that cubic expression, function rather, is 0 as x approaches I think 1, yeah. So that is what you need to do. So for this one, you just have to practice this yourself, okay? So normal stuff, you write for every epsilon greater than 0, there is delta greater than 0, such that the closeness to given point A is greater than 0 and is less than delta. So if that is true, it follows that the absolute value of f of x minus L is less than epsilon. Then you now substitute all these parameters and you follow the same step, okay? So this will be the end of this solution. So during the live stream next week, Saturday, so I think that will be 28, okay? So the same time, so we're going to look into the remaining 3 parts when you have a rational function, square root and cube root function. So how can you prove their limit? So that will be the part 2 of this video. So until then, enjoy yourself and practice a lot.